Imagine a city not on Earth, but on the moon. Not in a century, but within our lifetime. How do we build a self-sustaining lunar colony from scratch, right now? In this video, we go deep into the technology, engineering, and economics behind launching humanity's first sustainable lunar settlement. We'll examine the infrastructure we need, the challenges we must overcome, and how corporations and investors can drive the moonshot forward. Since the Apollo era, the moon hasn't been more than a waypoint or a symbol. But now we're entering a pivotal moment. With NASA's Artemis program pushing towards sustained lunar presence and private space ventures accelerating every year, the moon is no longer just a dream. It's becoming a frontier for real, permanent infrastructure. In fact, the window for beginning foundational construction is now. While we still have political momentum, falling launch costs, and advancing technology, transitioning from exploration to habitation demands new paradigms. Today's efforts can lay the groundwork that future generations will build upon. First, the timing is critical. The Artemis missions are not just going to put humans back on the moon. They're explicitly designed to begin assembling infrastructure for long-term presence. Through Artemis, NASA plans to develop lunar landers, surface habitats, power systems, communication relays, and robotic infrastructure. These missions set the stage for a base camp rather than short touchdown missions. Second, private space companies have lowered the barrier. With reusable rockets, commercial landers, and scalable launch economics, the cost per kilogram to the lunar surface is decreasing. As those costs drop, constructing a colony becomes more than a government-only mission. It becomes a commercial possibility. Third, there is a cascade of benefits that justify lunar colonization today. Scientific discovery, resource extraction, and serving as a staging ground for Mars or beyond. Science gains. The lunar surface preserves ancient solar and cosmic records. Geology, astrochemistry, and early Earth analogs all reside on the moon, waiting to be studied. Net resource potential. Lunar regolith contains oxygen, metals, silicon, and water ice hidden in permanently shadowed craters. If we can extract them, we reduce dependence on Earth supply. SITE, NASA discussion of in situ resource utilization, NASA. Then launch platform. Because the moon has about 1/6 Earth gravity, launching rockets from its surface to deeper space requires drastically less propellant. A lunar base could serve as a refueling and staging hub for Mars, asteroids, or outer solar system missions. These three pillars, science, resources, and strategic expansion, give tangible rationale for building today rather than waiting. Debunking misconceptions. Before we dive into technologies, we need to address a few common doubts. It's still science fiction. No longer. Projects like Artemis, CLPS, commercial lunar payload services, and corporate landers are actively laying groundwork. The idea of lunar infrastructure is shifting from blueprints to contracts. Too expensive to be realistic. Yes, it is costly, but cost curves are falling. Many estimates decades ago assumed 1,000 plus per kilogram to the moon. Now, with reusable rockets and commercial models, incremental infrastructure becomes somewhat more accessible. Humans can never live there long-term. The challenges, radiation, vacuum, temperature extremes, dust, are very real. But engineering techniques exist that, with sufficient development, can mitigate these. It's not easy, but it's not impossible. So yes, this is ambitious, but ambition is exactly what's needed. Technologies and systems for a sustainable lunar colony. Now let's get into the engineering backbone, the technologies that have to be solved or scaled to make a lunar colony viable. 1. Habitat structures plus construction materials, buried or regolith shielded structures. To protect from radiation, micrometeorites, and extreme temperature swings, habitats will likely be buried or covered under meters of lunar regolith. Using robotic 3D printing, machines can scoop, melt, or sinter dust to encase habitats. A recent project, Lunar Subterra, proposes a self-integrative habitat that starts underground and can expand upward, giving radiation-shielded living space immediately. Arxiv. Lunarcrete, mooncrete. A promising material is lunarcrete, concrete derived from lunar regolith using in situ binders or sulfur-based concretes. It avoids the need to ship bulky materials from Earth. The concept has been studied in labs and offers compressive strength viable for structural elements. Autonomous excavation and robotics. Construction robots will need autonomy to dig trenches, build blast protection berms, and lay foundation. Autonomous multi-robot excavation studies show teams of robots can interpret blueprints and dig protective berms. Landing pads and infrastructure. Landing pads must be designed to absorb rocket exhaust and minimize regolith disruption. One trade study on lunar landing pad costs estimated that constructing a pad with microwave sintering or polymer infusion could cost on the order of $47 million to $229 million, depending on transport costs. 2. Power and energy systems. Sustained energy is a core requirement. Solar power plus energy storage. Solar arrays on lunar poles or high sunlight zones would power the settlement during lunar daylight. But nights last for 14 Earth days, so storage or alternative sources are needed. Nuclear fission, compact reactors. NASA's kilopower is one example. A small fission reactor designed to provide sustained power even in the absence of sunlight. Proposals often include small reactors of tens to hundreds of kilowatts to megawatt scale. And fuel cells and regenerative cycles. Energy from daytime arrays can be used to electrolyze water, from ice, into hydrogen and oxygen, storing energy chemically. At night, fuel cells convert that back to electricity. Such closed-loop systems are being explored in terrestrial analogs. 3. Life support and closed-loop ecosystems. Water extraction and recycling. Ice in shadowed craters or subsurface layers is critical. Techniques include heating regolith or vacuum desorption to liberate water vapor. Once extracted, water must be recycled in closed-loop systems, air, hygiene, plant transpiration. The oxygen and breathable atmosphere. Electrolysis splits water into oxygen, for breathing, and hydrogen, fuel. Additional sources include regolith oxygen extraction, e.g. from oxides. Of food production. Initially, shipments from Earth will supply calories, but over time, hydroponics, aeroponics, algae bioreactors, and low-energy LED lighting will provide fresh food. Waste recycling and nutrient recovery must integrate tightly. Atmospheric pressure and shielding. Habitats must maintain Earth-like pressure, 1 atm, or lower, e.g. 0.5 atm breathing mix, depending on engineering. Multi-layer membranes, structural domes, and redundant life support will manage leaks. 4. Communication and data infrastructure. Moon-Earth relay satellites. Because direct line of sight may not always exist, e.g. poles, hidden craters, relay satellites provide continuous high-bandwidth communication. As local mesh networks. Wireless networks across the lunar surface for sensors, rovers, automation, likely using RF, optical comms, or laser links. Or data centers plus compute at the edge. Local compute helps with autonomy, AI, analysis. Because latency to Earth is non-trivial, many operations must be handled locally. 5. Automation, AI, and robotics. To reduce human burden, much of the colony's work must be automated. Construction and maintenance bots. Robots can inspect, repair, build, and manage regolith cover. Advanced AI can detect faults before they propagate. Autonomous transport and logistics rovers and drones carrying goods, managing supply lines, and distributing thermal loads. AI monitoring and anomaly detection. Predictive maintenance on critical systems, intrusion detection, environmental monitoring, and safety controls. Quantum-enabled control and cryptography. As the colony scales, secure quantum communication between modules and Earth becomes important, tied to your expertise in quantum. Sustainability and long-term viability. Sustainability isn't just a buzzword, it's essential. A lunar colony must become increasingly self-reliant. Maximize in situ resource utilization, ISRU. The fewer materials shipped from Earth, the better. Every kilogram launched from Earth costs tens or hundreds of thousands of dollars. At those economies of scale and modular expansion, start with a small seed habitat, then expand through modular units that share infrastructure, power, life support. Circular material flows. Recycle metals, water, air, nutrients. Waste must become input wherever possible. An adaptive and upgradable architecture. Design HAB modules to be upgradable, repairable, and reconfigurable. An environmental monitoring and protection. The lunar environment, micrometeoroids, plasma, cosmic rays, must be monitored and mitigated. A 2025 review towards sustainable lunar-based development stresses that energy systems, environmental control, and resource utilization must be integrated into a coherent architecture. Cost and economic models. No lunar colony is cheap, but understanding cost helps investors and strategists plan. Historical and published cost estimates. In 2009, CSIS estimated building a lunar base would cost $35 billion, with operational costs of $7.35 billion annually, assuming Earth-supplied resources. Earlier studies suggest more ambitious colonies could cost $50 to $90 billion over 25 years in real terms. Some speculative estimates range from $250 to $500 billion to establish a full moon colony with supporting infrastructure. As landing pad construction studies estimate costs for single pads from 47 melos to 229 melos, depending on transport cost assumptions. Long-term estimates of lunar products and life cycle cost models further show massive capital and operating expenditures. In short, tens to hundreds of billions in infrastructure, plus multi-billion-dollar annual operating costs are plausible. Economic potential and return paths, resource exports, helium-3, rare earth metals, oxygen, water. Space tourism and hospitality, high risk but high margin. Manufacturing in low gravity or vacuum, unique materials, fiber optics, MEMS. A telecoms are data infrastructure between Earth and Moon, relay services. An energy and power beaming, moon solar farms sending power back to Earth, very speculative. A space ref opinion piece forecasts that by 2040, lunar bases might export resources, support Earth economy, and leverage command control layers. For investors, the play is in scalable infrastructure, habitat platforms, power systems, ISRU mining hardware, robotics, rather than the colony itself. The role of corporations, private firms, and investors. Corporations aren't spectators. They can be prime movers in building the lunar colony. What corporations can do: build modular habitat systems, develop power systems, solar plus fission plus fuel cells, create ISRU systems, oxygen extraction, metal refining, develop robotics and automation platforms, space logistics and transportation, lander shuttles, orbital infrastructure, telecom and data services, relay satellites, laser comms. What investors should look for: scalable core technology, robotics, ISRU, power, infrastructure multiplier effects, components useful on Earth or Mars too, public-private contracts, NASA's CLPS, Artemis, Gateway, phased milestones, demonstration missions, prototyping, lunar builds. Investors benefit when they fund components, e.g., a power reactor or regolith processing plant, that are essential regardless of full colony scale. Governments also play a role via subsidy, contracts, regulatory frameworks, and international treaties, e.g. Artemis Accords. One tangible contract. In 2025, Thales Alenia Space and ASI signed a deal to build a multi-purpose habitation module for lunar outpost under Artemis. Combining public funding with private capital helps de-risk early phases. Challenges, risks, and roadblocks. Any lunar colony plan must reckon with serious obstacles. Engineering scale and reliability, redundancy, repair, failure tolerance. Systems that fail mean life-threatening results. And launch and transport bottlenecks. Until transport costs come down, each kilogram moved to the moon is expensive and risky. And thermal extremes and radiation without atmosphere, cosmic rays, solar flares, and micrometeoroids are constant hazards. Send dust, a regolith, Electrostatic, abrasive, clingy dust risks mechanical and life support systems. Harvest now, decrypt later models. For colonies using encryption, data harvested today might be decrypted later once quantum becomes viable. Security must be future-proof. Illegal and governance. The Outer Space Treaty forbids sovereign claims, but commercial use is ambiguous. Who owns lunar resources? Who regulates mining rights and trade? A human physiology and psychology. Long-term exposure to radiation, low gravity, 1/6 Earth, isolation and confinement pose health and mental challenges. Despite all this, the direction is clear: iterative, modular, scalable, and risk-managed deployment. A sample roadmap, phased strategy. 1. Demonstration modules in lunar orbit, gateway. Validate habitat life support, solar nuclear power, robotics. 2. Small habitat on lunar surface, 1 to 3 crew. Use robotics for base construction, begin ISRU and power systems. 3. Expand habitat plus resource processing, add modules for agriculture, manufacturing, fuel production. 4. Develop industrial zones, mining, smelting, telecom, manufacturing. 5. Full sustainability growth until the base is largely self-supplied with minimal Earth resupply. The first stages should aim for break-even or multiplier effect technologies, i.e. ISRU power systems, robotics, modular habitats. What you'll see by 2030 to 2040 if this works: 1 or more small-scale lunar outposts, likely at the lunar poles for ice access. Regular resupply missions, crew rotations, evolving infrastructure. Emerging lunar mining and power systems. Use private sector ecosystems around lunar supply, logistics, construction. Moon-to-Earth data, power relay, and commercial services. As some analysts project, by 2040, lunar bases may begin contributing exports and supporting Earth economies. We are standing at a historic moment. The moon is no longer a distant dream. It's a construction site waiting for the first blueprints. The technologies exist or are emerging. The incentives align, and the will is stirring. What has been fiction is rapidly becoming engineering. If you're a technologist, investor, or dreamer, now is your moment. Support lunar architects, fund ISRU and power systems, push for responsible regulation, and dream modular, scalable infrastructure. Because if we build right, humanity won't just visit the moon, we'll live there. And when that happens, the moon won't be the end. It will be the launchpad to the solar system. What do you think? Do you think we have what it takes to launch a colony on the moon? Leave your comments below. Follow the Tech Radar for the latest news and updates around AI, technology, and other financial and scientific topics. Thanks.